In this 8th lecture, we look at probability theory. First, we want to learn what the probability space is, get a little bit into history, and learn about the setup. Probability theory is the science of chance, a theory about randomness. It has many applications, from gambling to physics, statistics. It also plays an important role in discrete combinatorics, where it helps counting. Why do we need such a theory? One reason is that the reality is complex. Our models always just capture part of the entire thing, and randomness allows us to model the uncertainty from neglected parameters. Historically, the theory started first in the context of gambling. It was Cardano, whom we know from the algebra lecture already, wrote a first book about probability theory, the book on playing dice, Liber de Ludo Aliae. The gambling with dice illustrates well the situation. The dice falling process is a simple mechanical system, but computing the outcome would require not only the knowledge about the surroundings, but initial conditions, the shape of the table, shape of the dice. Since we don't know the outcome, we just assume that the probability to hit a number is 1/6. We also assume that the outcome of the second dice has no relation whatsoever with the outcome of the first. Abraham de Moivre also played an important role. Historically, he wrote the book The Doctrine of Chances. He already developed an early version of the central limit theorem, noting that successive binomial distributions converge to a Gaussian distribution. It's surprisingly well readable, this book. It was popular among gamblers also. But it was Andrei Kolmogorov who really put probability theory onto a firm foundation in the 20th century. By the way, if you look at Kolmogorov, do you not think you have seen the person already? Actually, he reminds me both of Steve Martin and Anderson Cooper. Here's the setup. We have a laboratory omega, as in set theory, where we had a universe X of things, but we call it now omega. The members of this laboratory are the individual experiments. The subsets are the events. There is a function p, which assigns to every event its probability p of a. For finite probability spaces omega, it usually is the cardinality of A divided by the cardinality of omega. This is a principle which already goes back to de Moivre, Laplace. We can get the probability of an event by counting the good cases divided by all cases. Here's an example. What is the chance to hit an even number when throwing a dice? As the event of throwing an even number has 3 elements and the entire laboratory has 6 elements, the probability is 1/2. Let's look at 2 dice. What is the probability that the sum of the 2 dice is bigger than 8? More challenging now because the probability space is bigger. We have to list all the possible 36 elements in the probability space and count the ones which lead to a sum larger than 8. Here we see all the 36 elements, and here are the ones larger than 8, and you see 2, 4, 6, 8, 10. There are 10 of them, so the probability is 10 over 36. So here's another problem. We have a card deck of 52 cards. In how many ways can we shuffle it? Other things, what is the probability if we shuffle it that we actually end up with the same well-ordered set of cards as we started with? So we have 52 possibilities to pick the first card and 51 to pick the second card, 50 the third, and so on. The result is 52 times 51 times 50, etc. The result is 52 factorial. 52 factorial is a huge number. It's 10 to the 68. You could never count that high. By the way, that number is pretty close to what Archimedes estimated to be the number of particles in the universe in his sand reckoner work 2,300 years ago. Here's a more complicated problem. Assume we pick 4 cards. What is the probability that we get 4 kings? So now we have to set up the probability space. The probability space consists of all possible picks of 4 cards. So that's also a large probability space, but we can count them. So we have 52 possibilities to pick the first card, 51 the second, 50 the third, and 49 the fourth. And so we multiply these numbers, but then we divide by 4 factorial because we don't want to look at the order. And then we have the good case, the event that we have 4 kings. There's only one good case, and so the probability is 1 over the size of the probability space, which is 4 factorial times 48 factorial over 52 factorial. This is the probability. With more information, like if we know the history of played cards in a card game, the probability space changes. This is used in card counting in the game of 21, as illustrated in the movie 21, shown here.
16 plus 17. Every card had a value plus 13. A high card minus 1. A low card plus 1. The rest plus 1. 0 plus 13.
In blackjack, there are various counting strategies. You have just seen in the movie. So the low cards are counted plus 1, 2 to 6, and the high cards 10, jack, queen, and king, and ace are counted minus 1. The others are counted 0. This is the end of the first part. In this second part, we look at the basics of combinatorics. Combinatorics typically deals with finite probability spaces, and we have to count things. So here are 4 main formulas. They cover many combinatorial problems. The first is the number of permutations. It's like shuffling cards. The second is the probability to choose k element from n without putting things back. That's when we choose a hand in a deck of cards. The third is the problem of picking elements with the same element, where the same element can appear several times. That's when you throw dice. And the fourth case is when we choose k elements from n, but where the order matters. That's like the Scrabble, building words in Scrabble. So here are 4 problems. First problem, Scrabble problem, where we have a word, candy, and we want to see how many possible words can be built with these 5 letters. And the answer is 5 factorial. You have 5 times 4 times 3 times 2 times 1. That's also related to the fourth combinatorial problem. When we have a smaller set, for example, we can ask how many words of length 3 can we form. So the first letter, we pick a first letter, is 5 possibilities, the second letter 4, the third letter 3. So we can count that 60. Or how many words of length 4 can we form? 120. Other way, we looked in class whether we can find some words with 5 letters different from candy. There was none, and actually I looked with a computer, there is none. Words of length 3, there is can, there is and, there are quite a few. Words of length 4, there are also a few like Andy. Well, assume now we have a monkey typing on a typewriter with 30 letters, 30 keys. Let him type 338,787 letters. What is the probability that he will write The Hound of Baskerville, which just appears to have so many letters? It's a novel of Arthur Conan Doyle. The chance is astronomically small. It's 1 over a Google to the 5,000. Astronomically small, but not 0. Here's the second problem. We pick 2 elements from 12, like in the Hunger Games. How many possibilities do we have? It's 12 times 11 over 2. It's also called binomial 12-2. It's a number which appears in the Pascal triangle. And the last problem is a Jim-Lock problem. You pick 3 letters from 40, but no repeats are possible. Then we have 40 times 39 times 38 possibilities to pick a code. If you can repeat, then we get just a 40 to the 3, 40 times 40 times 40 possibilities. Finally, let's look at the problem from lottery. Kind of if you have a mega box, in mega box we pick 6 from 48, and in Powerball we pick 5 from 69. Where are the chances bigger? And this is just a matter of computing these combinatorial numbers. 48 factorial over 6 factorial, 42 factorial of 69 factorial divided by 5 factorial, 64 factorial, and we see that Powerball has a slightly larger chance of picking the right winning combination. In the homework, you will work on a probability problem in the game of set. This is the end of part B. In this third part, we look at some paradoxa in probability theory. Some of them are surprising. The first is the Petersburg Casino. You're going to that casino, you play a game, you bet an entrance fee, and you win 2 to the n, where n is the number of heads which appear first in a sequence of coin tosses. What is a fair entrance fee? We do the experiment in class, but you see, if you do it yourself, that already betting $10 each time gives you a very hard time and you lose a lot. For example, if there's 3 times head appears and then tail, you win just $8, but you have paid $10, so you lose still 2. You only win if 4 times head appears. Another paradox is the foolproof martingale betting strategy. You go into the casino and you play roulette, you bet on red. If you win, you walk away. So you have won your money. If you lose, you double your bet. And if you lose again, you double your bet again, etc. until you win. Once you win, you have won still the initial entrance fee and you walk away. You always win with that strategy. Let's try it out. We'll go to an online casino and play. Can one compute the motion of a ball in roulette? Actually, some have done that. Use a smartphone, scan the motion of the ball, and have a computer in the shoe computing the outcome, and so get a better chance of knowing where things end up. And they made a lot of money, but they were caught. In Lotto, where balls bounce each other off, the motion is more complicated and more chaotic, and the computation would not more be possible. We will talk about chaos theory in a future lecture. Here's another paradox. It's a Monty Hall sensation. It's named after a game show. Here's a clip from that TV show. Assume there are 3 doors. Behind one door is a car, behind the others are goats. You are a contestant and choose a door. The host, who knows what is behind the doors, opens a door with a goat different from your door. Now you have the possibility to switch. Then the door is open. What are your chances of switching or without switching? Let's analyze that. So, as explained by Marilyn Beauce-Savon in a 1991 column, the story is very simple. If you don't switch, you obviously have a chance of 1/3 to win the car. This is the story without switching. Now, with switching, if you initially hit the door with the car, you will lose because you have decided to switch and chose the door with a goat. If you choose a goat, and the host will open the other door with the goat, you will hit the car because you have switched. So the chance of winning is 2/3. This is well explained in the movie 21.
All right.
Here's a related problem due to Martin Gardner. Dave has 2 children, one of whom is a boy. What is the probability that Dave has 2 boys? We just look at all the possible cases. There are 3 cases: boy, 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 girl, girl, boy, which have all the same probability. In this probability space, there are 2 where the second is a girl and 1 where the second is a boy. So the chance of having the second a boy is now only 1/3. Chance to have the second one is a girl is 2/3. Martin Gardner, who put the problem forward first, also put the second version. As a comparison, if you know the first one is a boy, that's different. And the probability of the second is independent, and of course it's 1/2. It's like throwing dice. So here is the story, just explained with the probability space. So we have 2 outcomes. One is a boy, so it's boy, boy or boy, girl. And 1/2 of them, in these cases, is a case where we have a second boy. This is a surprising twist. Assume Dave has 2 children, one of whom is a boy born at night. What is now the probability that Dave has 2 boys? The answer is surprising. Why the heck does the information that one of the boys is born at night influence the probability? Common sense says that it doesn't, but it does. So here's the set of events, set of possibilities. So you know that one of the boys is born at night. So there are 7 cases. We just look at all the cases where there are 7 cases. Now there are 3 cases where the second is a boy. So, now we have 7 elements. This is our probability space has 7 elements. These are the elements where one of the boys is born at night. Now we look at the cases where the second kid is a boy. These are the orange cases. There are 3 of them. So the probability is 3 over 7. This is a different probability than before. A nice paradox has been put forward by Joseph Bertrand. He deals with a probability space which is not finite, but it's a simple problem. So we throw a line, randomly a stick onto a circle. And what is the probability that the line is longer than the segment is longer than the length of the inscribed equilateral triangle? Let's just see that the problem is that there are 3 different solutions which all are convincing. The first solution just looks at the center of the segment. If it hits the circle of radius 1/2, then we have a line segment longer, otherwise not. And the circle of radius 1/2 has an area 1/4, so probability is 1/4. We can also just rotate the stick around a point. Doesn't matter around which point we do it. They all have the same by rotational symmetry. It doesn't matter. So we have now a sector of 60 degrees where we have a line segment longer, and 2 sectors of 60 degrees where the line segment is shorter. So the probability is only 1/3. The third solution, kind of, you translate the line, and you see that there's a segment of length 1. This is the diameter of the orange circle where the line is longer, and the other 2 has also length 1 in total where the line segment is shorter. So the probability is 1/2. So what is the right answer? The solution is that it depends on the probability space. If you run the experiment, it depends on how you do the experiment. Here's another paradox. It's called the birthday paradox. A little bit surprising. If you teach a class of 23 students, what is the probability that 2 of them have the same birthday? Let's compute that. So it's good to compute the complement. We have 365 days, and the chance of all having a different birthday is 365 times 364 times 363, etc., until 343. And then we divide by 365 to the 23. So that's our computation. It's smaller than 1/2, which means the odds to have 2 students have the same birthday is already bigger than 1. So such math explains prices and coincidences we see in daily life. There's a whole book about that. So here examples from that book. The Bulgarian lottery randomly selected the winning numbers 4, 15, 23, 24, 35, 42 on September 6, 2009. 4 days later, it selected the same numbers again. Or the North Carolina Cash 5 lottery produced the same winning numbers on July 9th and 11, 2007. Strange, not according to probability theory. This is the end of part C. In this last part, we look at random walks. It's a large theory, and we cannot get far, but it leads us to modern probability theory and also at the frontier of the subject. Random walks belong to the subject of stochastic processes. What we do is we add random variables. A random variable is just a function from the laboratory omega to the reals. We can now add up such random variables. For example, if you have x1 is the value of we get when throwing a dice the first time, x2 the value when we hit the dice the second time, etc. And then we add up these numbers, we get the random walk. If Sn is the position at time n, then we can draw the partial sum. This can be our winnings, for example, when walking randomly up and down. And so that's why it's called a random walk. We can also do that in 2 dimensions, or change also x and y coordinate. So this is the path of a confused mouse, drunken mouse. And surprisingly, the mouse will always return back with probability 1 again and again. In 3 dimensions, we can look at the tipsy sparrow flying around randomly. But now the sparrow will not return with probability 1. It will fly to infinity with probability 1. That's why we see much more mice than sparrows. Here's a deterministic version. It's a thing which is still very much under investigation. It's the curlicue problem. You drive in a desert. So you drive a mile, then you turn the wheel by a fixed angle. You drive another mile, then you turn the wheel by a fixed angle. And you drive again a mile and turn the wheel by a fixed angle. And this fixed angle is always, you turn the wheel always in the same direction, and then we wonder where we end up. So here is an example. So this produces a random walk. In this case, the angle of rotation is the golden mean. And what we see is that these random variables are no more independent. It's not really random, so we have a deterministic process. But what happens is you get this beautiful path, which is a kind of a fractal type structure, and this is called the curlicue. The first important theorem is the law of large numbers. It tells us that if you look at the average winnings, we get the expected value of the random variable. So this is a very nice theorem, and it can be generalized in various ways. And then there is a version where if you scale not by n but by square root of n, then what happens is the distribution will become the Gaussian distribution. That's why we see so many Gaussian distributions, because processes are very complicated. We add up many independent variables. And then there is a refined version. It's kind of the ultimate theorem, the law of iterated log, which tells that if we kind of just take a little bit more, scale a little bit more, we get to a bounded interval in the limit. We can add other random variables. Something I recently worked on is if you add random variables which have infinite variance, and for example you take the cotangent of a function and you add these things up with an irrational rotation. We add up with random walks which look very different from the random walks seen before, and it kind of looks a little bit more like financial data, where you have sometimes really kind of crashes, very strong changes of the with this small probability, but they happen from time to time, and that also happens in this random walk. Another riddle which is unsolved is whether the digits of pi behave in a random way, so we can use them to make a random walk. And also count, we can make the statistic, we can count how many times does the letter 5 appear in the decimal expansion of pi, and the measurements are that all these digits appear with the same frequency, and that even more these digits appear random, but nobody was able to prove this yet. So there are many applications. One of them is quantum mechanics. That's from a movie, Serious Man.
From which it proves we can't ever really know what's going on.
Also applications, of course, in statistics. This is from the movie Moneyball.
Games and allow no more than 645 runs.
Just again about the history. So here are a few pioneers in probability theory: Cardinal, Fermat, Pascal, Laplace, de Moivre, and Kolmogorov. And there is a huge literature about this. We have just scratched the surface. I've also written once a book on probability theory and stochastic processes. You can check it out. It can be obtained freely from my website. That's the end of this probability lecture.